Following on from our previous lecture on key attributes of distributed systems, what we're going to look at now are the different models for inter-process communication. The most basic type you can have is what's called a remote procedure call, or an RPC. The RPC programming model is a first early generation approach to sharing computational services, i.e. resource sharing, between different nodes or components of a distributed system. The model relies on a simple request-reply communication protocol, resulting in a fully coupled communication between applications. The underlying RPC support varies with the programming language and is therefore not amenable to heterogeneous computing. So let's look, for example, what does it mean to say that we have a fully coupled communication between applications? What that basically means is that procedure B over on the right and procedure A are tightly coupled in the sense that procedure A needs to know about the internal workings of procedure B in order to call it. In addition, procedure A and procedure B are running as two separate processes. Therefore, the information from procedure A, even on the same computer, has to be marshaled, i.e. converted into a format that procedure B can understand. That information needs to be sent to a function in procedure B, which executes and returns via some, again, marshalling protocol, a result that procedure A can actually accept and then do something with. This only works at a binary level between existing, between programs written in the same programming language. So these are an example of a homogeneous inter-process communication mechanism and is very, very limited. A more refined approach is the object-oriented model, in contrast with the remote procedure call, which again in terms of parametric capability can only handle things like structs and arrays as the most complicated data structure. The object-oriented model talks about the concept of a method as opposed to a procedure and has a lot of commonality with the RPC, but allows a greater degree of loose coupling. Indeed, not all of the methods of an object need to be remotely invocable. We can basically flag some as being remote methods and leave others, even public methods, as local only. However, the object-oriented interprocess communication mechanism allows for what we call parametric polymorphism. In other words, that the parameters that we pass to the methods as arguments, and indeed the return types from those methods, can themselves be abstract types, therefore enabling full polymorphism. It is definitely a far greater and more modern approach than basic RPC, remote procedure call. An example of this would be remote method invocation, Java RMI, which underpins a lot of the J2EE EJB framework. Using concrete classes as the basis for remote method invocation, even in an object-oriented model, is not a great idea. It will be far better at the bare minimum, okay, to extract an interface from an object representing the core public remote methods that you want to expose to client applications. This model, therefore, then takes advantage of the notion of abstraction, and by extracting an interface from a concrete class and exposing that for remote invocation, we're effectively giving the user a contract which we cannot change without adversely impacting them. Therefore, the interface gives a high degree of stability and ends with a less volatile system that has all of the benefits of the object-oriented model, plus additional elements such as abstraction. The object nirvana, as we spoke about this the last day, the object nirvana was the notion that we could go with complete component-based development, the publication of discrete distributed systems consisting of effectively services that were based on components. These are more coarser-grained ideas than classes. It's the interaction between a number of different classes. Think, for example, maybe a package as opposed to just one or two classes. That the component could act like analogous to a piece of Lego, and we can basically click it or use it in our own application with the minimum of knowledge required as to the internal workings of it. In other words, we have the separation of interface and implementation. So this follows on from our object-oriented model onto our interface-based model, that the component-based model itself should be described by an interface that exposes fine and indeed coarse-grained aggregate methods of a number of different classes that make up a full component. So in other words, it's scaling up a bit. The idea of Object Nirvana was that we could build a distributed application by aggregating disparate component-based services that were distributed physically in different places and just reuse them with a minimum of knowledge as to how they actually worked internally. Finally, we get to the notion of the service-based model itself. And again, this just leads on directly from the interface and component-based model. A service-oriented model allows services themselves to be described, hopefully in a platform and language-neutral manner. It's completely independent of the programming language and the underlying operating systems. These characteristics are key then to understand the interconnectivity of devices in a modern, heterogeneous, distributed application. The service is encapsulated to the greatest extent possible to represent a unit of business work or a core responsibility. It's more than component-based. What we're doing now aggregating different components, okay, to build full-blown services, which themselves can be orchestrated and aggregated together to create complex distributed systems. The key ideas here, however, are the independence of programming language and platform. And in the context of that, it does raise issues as to how is this possible. Fundamentally, there's only three real ways we can do this. We can have a binary level protocol, a lingua franca that we all agree to use. We can have middle of the road, like bytecode in Java, or we can have something very high level, such as text Unicode. In the case of the service-based model, the preeminent approach today is to use text-based inter-process communication, marshalling in the form of JSON, that's your JavaScript object notation, or XML and XML schema in the form of SOAP, your Simple Objects Access Protocol, and WSDL, an XML way of describing a service interface. Now we will look at all of these different models except the remote procedure call throughout this module. The final thing we'll talk about here today, and we're just going to briefly touch on this, it's just the evolution of how we've gotten to the idea of the Web 2.0, web services, whole cloud-based platforms like Heroku and things like this, and the whole now Internet of Things, and the capability of generating large systems that are comprised not just now of actual computer servers, what we would have thought of in the past, or desktops, but even sensors and these various other types of devices. So we moved basically from a high computing HDC environment and a high performance computing environment to a point where we have peer-to-peer programming, clustering, massive parallel processing. Then we got to the notion of computational data grids about 10 to 15 years ago. And since then, the techniques and technologies that have emerged are now Web 2.0 web services and the service-oriented architecture, which again goes back really to 2000, maybe slightly earlier, and the work of IBM at the time, the Internet of Things, RFIDs, sensors, and the actual virtualization of the services in clouds. Again, think of your Amazon Elastic Cloud or Heroku cloud services. That's it for this little session. We're going to take it up in the next lecture. We're going to look at different architectural models for distributed computing, and that will include cloud-based models. And I'll talk to you all then.